Today we're going to be talking about transformations of the sine function. So we have previously graphed the sine function, talked about some key features of the sine function, and you're going to notice that this top graph right here, or this blue graph, is the sine function. Now there is a red graph underneath. Now what the red graph represents is sine of x minus 3. This minus 3 is very, very important. This is a vertical translation. Now, vertical means up and down, and I'm sure, like you can guess, you see a minus 3, and that makes sense that it's shifting down 3 units. So if you can see, every key point on this graph, so my 0, 0, my 91, my 180, 0, my 270, negative 1, and my 360, 0 has been shifted down 3 units. If we're talking about the domain and range, so we have already talked about this. If I'm doing the domain and range for my function sine of x, f of x is equal to sine of x. My domain is xer, so I can have any kind of x value that I want. This sine wave will go forever and ever. But my range is a little bit different. So my range is yer such that, so my range is my y values. My lowest y value is negative 1, and my highest y value is positive 1. Now, when I'm talking about my domain and range for f of x is equal to sine x minus 3, I know I used g of x there, but it doesn't really matter. My domain is still the same. So my domain is still xer. This sine wave will go forever, but my range changes. So my range is yer such that, now when I look at this new red function, the lowest that I can go is negative 4, and the highest that I get is negative 2. Now this makes sense because we know the whole function has been shifted down 3. So if I was at negative 1 and I moved that down 3, I'd get to negative 4. And if I was at positive 1 and I moved down 3, I'd get to negative 2. The last thing that I want to talk about for these two functions is the equation of the axes, the amplitude, and the period. So the equation of the axes is that middle line. So when I look at my original sine of x, my center line is at 0. So y is equal to 0. And my new one, the center line I have drawn in a dotted line here, is y equals negative 3. So again, it was 0, it's now negative 3, which represents my shift down 3. My amplitude hasn't changed. So my amplitude in the first graph is 1, and the amplitude in the second graph is still 1. And my period also hasn't changed. I'll just switch to a highlighter here, but I have one period, so reach the top, back to the middle, reach the bottom, back to the middle, and that took 360 degrees. The exact same thing for my second function. Reach the top, back to the middle, reach the bottom, back to the middle, 360 degrees. Now, just to finish off this vertical translation page, I do want to mention that we call a vertical translation C if we're thinking about adding a variable to it. And so what we're going to end up with is f of x is equal to sine of x plus c. So it's always this plus or minus c added to the end of the function if it's a vertical translation. On this slide, we're going to be talking about horizontal translations, so shifts right and left. Our example is basically the exact same as last time. So we have our original function in blue, that's our sine x, and we have our second function in red. In this case, it's sine of x minus 60. Notice the minus 60 is in the bracket with the x. This is the main difference between our d and c value. So our c value is a vertical shift and our d value is a horizontal shift. So I'm going to represent this by x minus D. Now, this one is a little bit strange. It is a little bit backwards. So if we have a minus 60, it actually means a shift right 60. A lot of people are going to think it's left, just like when we move our quadratics, it's the opposite sign. So this means that every key point has been shifted right 60 degrees. So I've learned a little bit from the last slide, and I kind of set this up a little bit better. So now we're going to be comparing the two equations, and I've made a chart for you. So when we're looking at sine x, again, our domain is just XER, and our range is YER, such that y is between -1 and +1. Our axes is at y equals 0. We have an amplitude of 1 and a period of 360. So all of this was the exact same as the last slide. That's why I went through it so quick. Nothing changed. Now, the things that are going to change are in our new red graph here. So our domain doesn't change. Just because we move something right or left, it doesn't change anything at all. Our range actually hasn't changed either. So since there was no shift up and down, our maximum and our minimums are still the exact same. So our range is the exact same. Our axis is also the exact same. Again, no vertical shifts means no change in axes. Our amplitude is still 1, and our period is still 360 degrees. Now, I do want to go over this one a little bit. Our period might confuse people. So our period starts at 60, hits its point at the top, goes back to the middle, hits the min, and goes back. And it's ending at 420. Now, this is still just 360 degrees. So it starts 60 degrees later than our original sine, but it ends 60 degrees later, so it's the exact same period. Our last example here, now we have their example. The last example says the graph of f of x equals sine x has been translated to the right 30 degrees and up 4 units. So we're going to be writing our equation here. So we're going to have y equals, or f of x equals, it really doesn't matter which one, sine of, I see that I'm going right 30. If something is going right 30, it means we need a negative 30. If it said left 30, it would be a plus 30. Now something is going up 4 units, so I need a plus 4. Now for those of you that like to keep good notes with all of your variables, this is going to look like sine of x minus d plus c. D is our horizontal translation, and C is our vertical translation.